Welcome to another session with my Tangerine Tiger. Hey, you're not looking at me. Stop. I can see what you're looking at. There we go. Now you can concentrate on me. At the last session, we dealt with comparisons between the RF and the glass tube. Now, the magic has disappeared for me because I was hoping to be able to make this a really fast photo engraving machine, but as it turns out, it's never going to be able to do photo engraving, not proper photo engraving. Now, I know the big companies claim that they can do photo engraving, but what I'm going to do today is to sort of go through the fundamental principles of photo engraving and show you how they do it and how it's not proper photo engraving. Now, I've watched a lot of their videos about photo engraving in the hope that maybe I'm missing some tricks. It only confirms what I've believed all the way along. They don't really understand what photo engraving is. Now, I know that sounds a bit arrogant. Please excuse me, but I've spent a lot of time trying to understand how to get the best out of these machines, to get as close to photo engraving as I possibly can. And what they're doing is not. It's a compromise. So today we're going to go through the principles, and hopefully I'm going to persuade you that you'll never really be able to do any successful photo engraving with an RF laser. Unless, and this is where those with big ones really win. Let me rephrase that. Big pixels don't mean a lot. Big pictures do mean a lot. And so consequently, I'm going to go through the basic principles of graphics. Now, not only have you seen my rather dodgy artwork, I'm also not a graphic artist either. But I have had to learn quite a few of the skills and techniques that graphic artists have to go through. I still might get a few details wrong, but the essence of what I'm going to tell you is about correct. It's a lot better than the magic, the mystery, the tricks, the mistruths and the myths that you'll hear when you watch any of the big companies talking about photo engraving. So I watched a very long session recently, and the guy was really talking a lot about the cameras, the need to produce a wonderful picture, high DPI. No, cameras don't produce DPIs. Laser machines produce DPIs. Cameras work with PPIs, the same as monitors work with PPIs. It just shows you the level of, I hate to use the word ignorance, but lack of knowledge is probably better to use. So hopefully at the end of this session, you might have a bit of a decent understanding about graphics and how you are never going to really succeed unless you use a few of my tricks with an RF machine. Who knows? Perhaps the big boys will rewrite their software based on some of the stuff that I'm going to tell you guys. So I'm hoping at the end of this session we'll be able to jump onto the machine and convert some of the images that I'm going to produce of this young lady into reality, and you'll see what the end results are. Now, a couple of sessions ago I tried to reproduce this image in a fairly basic form without any retouching or any modification to the picture, just straightforward conversion to grayscale and then to a dithered image. They varied from abysmal to half decent, and we got to something that was pretty good but not perfect by using some rather strange graphic techniques. This looks like a very high resolution studio portrait picture, which it is. I mean, it's great. The focus is on the eyes and the mouth and the teeth, and everything else is disappearing into the background except her fringe. If we take a look at the properties of this picture, you'll see that it's got 162 megapixels at the top there. I want you to remember that number, 162 megapixels. Bear in mind it says pixels per inch, PPI. That's the number of pixels per inch that are on that image. And I want you to make a note that it's roughly half a metre wide and 3/4 of a metre tall, that picture. I know it isn't on my screen, but that, if you were to turn that into reality, that's what it would be. So I'm now going to change this picture to 1 pixel per inch. What do you think is going to happen? OK. There we go. You say, but hang on, that's the same picture that you had before. No. Let me just show you. Image size, 162 megapixels, exactly what we had before. But this time, look at the size, 156 meters wide and 234 meters tall. That is a huge billboard, a very big billboard. And the point is that I changed these pixels to 1 inch square. They don't look 1 inch square, but that's because a pixel can be whatever size you want it to be. You would have to view this from about a mile away to see that quality picture. Now, as you started walking towards this picture, you would see this sort of thing. Now look, there's my 1 inch square pixels. That's the first thing I need you to understand. A pixel can be whatever size you want it to be. The only problem is, the bigger the pixel, the further away you'll have to be to see the quality of the picture that you're producing with those pixels. Okay, so let me do something else now to the standard size, and let's resample it this time, and we'll constrain the proportions. And this time what we'll do, we shall keep it at 300 millimeters per inch, and we will change the width to 5 millimeters. Yeah, I know it's small. Fit on the screen and see what we've got. Now that's what you thought you were going to get the first time round. The point is here, as I tried to explain to you at the beginning, size does matter. We've still got 300 pixels per inch on this picture. But the picture is very, very small. So we're using less pixels per element. So for instance, her eye, if you take a look at her eye, it's now only 1, 2, 3, 4, 5, about 10 pixels wide. So it's a pretty crude picture because we have not got enough pixels to, if you like, give us all the detailed information that we're looking for. Now if you squint your eyes at that screen, your brain performs magic, and all of a sudden you can see the picture as clear as daylight. It's only when you open your eyes and you can see the detail on the screen that you realize that, hey, this is not quite what it seems. So that's the other important thing that I want you to remember. Graphics is all about you fooling your brain. What I'm going to show you now is the basic technique by which all the big companies approach this graphic problem. They've all got their own bits of software, or they'll tell you to use this Photoshop or CorelDRAW or CorelDRAW, whichever you say, tomatoes, or you've got something like GIMP. There are many bits of software which will perform the same tricks as those that I'm going to show you here in Photoshop. So the first thing that I'm going to do is I'm going to convert this image to something that the big boys say you should do, which is high resolution. You know, they claim that they can produce 600 or 1000 DPI images. Okay, let's do it. File, new. We'll make our picture 180 millimeters wide. We're going to produce A4 size, 180 millimeters wide, 250 millimeters tall, and a resolution of 600 pixels per inch. I'm now going to drag the image into here. Control minus, and then we'll do a shift key and drag one of the corners to make it approximately the size that we want. There we go. And then we'll just change tools to apply transform, and then we'll do view, fit on screen. So there we go. So that's now a 600 pixels per inch picture. Doesn't look any different. The only difference that you would possibly see if we looked closely is there may be now in this picture at 300 pixels per inch on the right hand side, you may find that there may be 1000 pixels across her eye. Whereas on this picture we may have 2000. So there are more pixels defining every element of the picture on the left hand side. We've not changed the information or the fidelity of that picture, because we started off with a big picture, if you remember, which was 500 millimeters wide and 700 millimeters tall. We've now changed the picture to double the resolution from 300 to 600, but we've made the picture smaller. So we're able to make our picture bigger with more pixels in it because we've decreased the picture size. Some of the videos that you'll see will spend a lot of time working on the coloured picture to bring the colour right, to bring everything correct. Hey, forget it. We're not going to be working with colour. What we're going to work with is black and white. But as an intermediate stage between black and white, we've got to get to something called grayscale. We could, at this stage, go into the image and we could do image adjustments. And one of the very powerful image adjustment things is shadow and highlight. Well, okay, look. I could mess around these to my heart's content to try and bring out various aspects of it. But this is a very well lit photograph and I don't need to play with this. So we should just do cancel and leave it as it is. If I zoom in on this, we can see we've got lots of different shades of grey in that image. Again, we can't work with shades of grey on the laser machine. We're going to burn some mark on whatever material it is. If it's on slate, it might be grey. If it's on acrylic, it might be white. If it's glass, it's going to be white. If it's onto paper, it's going to be brown. If it's onto wood, it's going to be brown. We're going to get only one colour to play with. It's whatever the colour is that we can burn onto the material that we're going to use. So grey is no good to us at all. We've got to turn this into a binary picture. That means two colours, the background colour and the foreground colour. And we do that by something called the dithering process. Image, mode, bitmap. Flatten the layers. This is where things get very interesting, because what I would normally do with this picture is to do something called a diffusion dither. We've already got 600 pixels per inch in the image, and so we'll say OK, and there we go. So that's now a black and white image. For those that you are not familiar with this, you're going to say, but no, that's a grayscale image. Cast your mind back to something I mentioned at the beginning of this video. Your brain is very, very good at telling you lies. Your eyes cannot see the detail in that picture, and therefore you are creating a false image of what that picture actually is. Let me zoom in and show you what that picture actually is. Those are pixels, 600 pixels per inch, and they are black and white. Black is what the laser will burn. So that's a set of Morse code signals to turn the laser on and off. Black being on and white being off. Now, we talked about this before, but hey, it's no bad thing to reinforce it. Now I hope you can see my little cursor moving around there on that single pixel. As it comes across from left to right, it's going to hit that edge, turn the laser on, and as it turns the laser on, it will burn a dot. That's all your laser can do. It can't produce square shapes, it can only produce round shapes. So it's going to turn on, and at that moment it's going to have half a burn dot hanging out the side of that pixel. And then it's going to traverse across that pixel with the laser on, and then it gets to the other end where white says, okay, turn it off. But by the time it gets to that interface there, black-white interface, we've already got half the beam hanging out the other side of that pixel. Although I'm calling for the computer to burn one pixel, effectively what it's done is burn 2 pixels, half before plus the pixel and half afterwards. Now the problem with that is we're going to fill some of the white that's there. And so if we take a look at this pixel before it, we've got half a pixel in front, half a pixel behind. This one's half a pixel in front, and this one's half a pixel behind. This one's half a pixel in front. Look, it's going to go black, 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 black. although the laser switched on, off, on, off, on, the net result that we're going to get on our material is black, 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 black. And then we're going to get black here. Oh, we're going to get 1.5, 2 pixels there, which are white. And then we're going to get half out here, half out here, half out here. So we're going to get a huge amount of black in here because we've got lots and lots of single pixels. Single pixels will effectively tell the laser to burn 2 pixels. So we're not going to get the correct relationship between black and white. The relationship between black and white is the thing that is going to fool your eye into thinking that you are seeing a shade of grey. And as I zoom out, you will see there's a huge amount of white in there that you can see, because that's her face. It's a shade, a very light shade, whereas when you get to her nostrils, we've got a lot of black. Well, we're not going to get a lot of black in that light area. We're going to get a lot of black in that light area. So the picture is going to be very, very overburnt. Now, the only way that you can make that picture lighter is to lighten the image to start with. Let's just show you what I mean. Now, if I come back to here and I do my image adjustments, brightness and contrast, no, let's do shadow and light. Net result is the same. So there we go. Look, we're going to make that nice and light. And this is one of the things that you'll always be told when you work with an RF machine. Yeah, look, we need to make this slightly lighter than normal. Why? Well, let's just convert that picture and I'll show you what's happened. So effectively what we've done, we've lightened the picture to remove a lot of the black pixels, so that those black pixels that do get turned from 1 to 2 pixels will not distort the picture too much, and will bring the picture back to a more normal type of shade. Whether you're using an RF laser or a normal laser, if you want to lighten your picture, generally don't just try and turn the power down, because that won't always work. Go back to your picture and make it slightly lighter. Reduce the number of black pixels in the image. Now, I'm totally confident that the guys that are selling these machines, these RF machines, are tackling this photographic engraving problem completely the wrong way round. Number one, I don't think they've taken into account the response time of their machines and the fact that their pixels are not 1 pixel but 2 pixels. So here we've got a table of typical focal length lenses. Now, most of the time the lens that they will be using on their machines will be a standard 2-inch focal length lens. Okay, sometimes you'll be able to get a 1.5-inch focal length lens, but hey, a 1.5-inch focal length lens is 0.003 of an inch, thousandths of an inch, 3/1000ths of an inch. Now in terms of millimeters, that is 0.075. Now a 2-inch lens has a 1/4 thou diameter footprint, as they call it, or spot size, and people assume that that spot size is supposedly the smallest spot that you're going to be able to burn on your paper. It's very much theoretical, because I would like to see somebody burn a 1/4 thou dot on a piece of wood or paper or card with a 2-inch lens, and it for only to be 0.1 or 0.004 inches diameter. It's almost certain it's going to be around about double that, 0.008, 0.006 inches, or anything from 0.1 to 0.15 millimeters. Okay, so what's the importance of that? Well, let's just stay with the theory at the moment, and just let's assume that we're able to produce a 0.1 dot with a 2-inch lens. We've got this image here set to 600 pixels per inch. 1 inch is 25.4 millimeters. So if we divide that by 600, it will tell us what size each one of those pixels is, and it happens to be 0.042. Now that's less than 0.002 inches. We're going to produce dots, if they're theoretically possible, 2.5 times the size of the pixels. If you look carefully up the top left hand corner, I've got a square that I'm moving around, and that square is 3 pixels by 3 pixels. That's the size of the dot that I'm going to be putting down. So let's see that line of single pixels there. The first thing that happens is when the computer starts, it's going to do that. And then it's going to move along to the next pixel, and it's going to do that. And then it's going to move along to the next pixel, and it's going to do that. So all I'm going to do across there, I'm going to produce a 3 pixel line. I mean, it's not going to take any notice of those black and white spots. I'm just going to produce a black line. Because I've told this to move down at 600 pixels per inch resolution, it's going to move down 1 pixel. Dip. So it's going to go back to the beginning, and it's going to move down 1 pixel. And then it's going to do the next line. Scan, scan, scan. Oh, it might leave a little space there. Look. Scan. Fill that one up. Fill that one up. Fill that one up. So there we go. So we've got nearly 2 black lines now. And then we're going to move down another pixel. So I hope you're getting the idea here. My dots are not the same size as the pixels. So there is no point in making a high resolution picture that you can't actually copy. The simple, very simple rule for good quality photo engraving is 1 pixel equals 1 dot. Or turn it on its head, 1 dot is the size of the dot that you can produce with your machine, with your lens on that material. You have to find out what that size is to start with. Because if it happens to be 0.2, you've got to set your picture to 25.4 divided by 0.2 millimeters equals 127 ppi. I hope you're getting the idea now. Pixels can be as big or small as you want, but at the end of the day, you can't copy pixels. You've got to make the pixels suit the size of the dot that you can produce with your machine. So that determines the resolution of the picture that you can reproduce. How do these guys get on with 600 dpi? How can they manage that? So let's go back to our grayscale image. I'll show you how an RF picture is normally composed. Image, mode, bitmap. Now when we get to this stage, Photoshop, along with lots of other packages, have got a choice. We've used diffusion dither, which is a lovely random pattern of dots to simulate the grayscale effect that you see in this picture. There are many different types of dither, which we'll come on to later, but this is the one that is normally used for RF work. We've got it set to 600 pixels per inch, which we know that we can't produce because we're going to produce dots that are 2.5 to 3 times the size of those pixels. Right, now here we've got a further stage. We can choose various numbers here, lines per inch. You say, what on earth does that mean? Well, it'll become obvious in a second. Let's leave it at 25. I could make that 22.5, for example. And we'll make the shape round. What on earth is this guy talking about? This is another way in which you can produce a simulation of grayscale. Now, if you squint your eyes again, you'll see that it looks like a perfectly normal grayscale picture. But then again, it looks as though, you know, we're looking at it through a net curtain. That's not a bad description, actually, because if I start zooming in on that picture, what you'll notice is that we've got black dots and we've got white dots. If you look carefully, you'll see that whether they're black dots on a white background or white dots on a black background, they vary in size. That's absolutely ridiculous, because we can't produce different sized dots with our machine. All we can do is produce one size dot, the best size dot that we can. We can make the dots bigger or smaller by changing the lens and by changing the focal distance, of course, but we can't keep changing the focal distance to change the dot size. So let's zoom in a little bit further and see actually what's going on. Aha! So that's actually what's going on. Look, we're producing blobs made up of pixels. So we're no longer looking at single pixels. Let's zoom in a little bit more. So now what we've got, we have no or very few single pixels. So my double pixel problem tends to disappear. Well, it doesn't disappear completely, because I'm going to produce a dot that looks like that, and then I come to the other end and I'm going to produce a dot that looks like that, and then when I come back from the other direction I'm going to produce a dot that looks like that and a dot that looks like that. So my dots are actually going to get bigger by half a pixel all the way, and they're going to get multiple burns, because look, I'm not just clearing one pixel, I've got a pixel that's 3 times taller. So when I come to the bottom here, I'm going to get that. So if you look at my big blob that's been, where every pixel has probably been burnt 3 times, and it's got an extra half a pixel hanging out the end and the top and the bottom, yeah, it is going to affect the ratio of black and white, but not by the same huge amount that it does with a normal diffusion dithered picture. That is how they tend to get away with high resolution. It's not really a high resolution picture. It's a polka dot picture which has been burnt many times. It takes a long time to produce, because every line, every pixel has to be burnt, and every pixel was burnt 3 times at least. Even if I replicate that oversized blob all over this picture, it changes the relationship between black and white a bit. But again, we've got a lot more white in this picture, so if we were to slightly emphasize the lightness or brightness of the picture before we started, we could compensate for that. I'm going to drop into a piece of software that I absolutely love. Although this doesn't support RF tubes at the moment, it's got a great set of graphics demonstration software in here, which will illustrate lots of great things about different sorts of dithering processes. Now here's our young lady, which has been imported in as a coloured photograph, and it automatically strips away the colour for us. Now, if we look at the parameters, I'm first of all going to choose different sorts of dither here. The first one is called dither. This is very similar to the Floyd-Steinberg dither that I've been using in Photoshop, where it's called diffusion dither. Okay, nothing has changed, because in this software you don't mess around with the picture, but you can see the signals that are going to go down to the laser by doing a preview. Now I'm just immediately scroll the mouse, because that way I can get an enlarged image of it. It doesn't have to keep building. There we go. There's a nice representation of what we've seen before. This is not exactly the same as the diffusion dither, because we've got lots of single lines here. Can you see that? That's going to be challenging for a glass tube laser, switching on and off that quickly. Everyone is virtually a single pixel by the look of it. Let's just make sure we're scrolling a bit further to see whether it's not an aliasing pattern on the screen. No, most of those are single pixels. Look, there are a few doubles, but that's it. So that's what a dither pattern looks like in Lightburn, which, to be honest, I wouldn't use. So if I switch on pass-through here, then it will take whatever image I import, and it won't mess around with it. It'll just output exactly the signal that comes from Photoshop. We'll take a look at something like Atkinson. So how does Atkinson work with this image at 600 dpi? We've got a lot of long lines. Again, everything seems to be broken up into little teeny weeny 1 and 2 dot pixels. Let's take a look at another one. These are all basically, as you look, they're diffusion dithers, but they're done with different algorithms. So let's take a look to see what Jarvis looks like. Well, it's a little bit more interesting. We've got a few long lines in there, but not many of them. Still lots of single pixels and double pixels. By that I mean to say we can see what the pixel size is, because look, we've got a gap there which is about half the width of the line. So that implies that we've got a pixel, 2 pixels, a pixel, 3 pixels, pixel. Do you see what I mean? You can work out roughly what the pixel size is on here. Let's take a look at this halftone. And there we go. Look, you can recognize that now from the image at the bottom. So remember, every one of the end of those black lines is going to grow by a pixel. So it's going to shrink the whites, and every one of the blacks is going to shrink the whites as well, because it's going to grow longer. So whichever way you look at that, you're going to decrease the white in the image. That means you're going to have to overcompensate on the lightness before you try and do this dithering process. And of course it gets worse than that, because every one of these lines is going to be burnt 2 or 3 times. If we're not careful, we could finish up with barbecue. That would be for a more powerful machine. For my 20-watt machine, this may well work very well in terms of getting me some colour, because with a single dots process I can't get enough colour to run at speed. So it's very convenient to use this package to show you what the signals are that are going down to turn the laser on and off. So every dither has its own pattern, and it appears that the only realistic pattern for an RF is this blob pattern, what they call halftone printing, which is the original process that they use for producing newsprint. When you look at some of the videos of them producing images, they're more like cartoons than photographs. Here I've got an image that's been produced by one of those pieces of RF dedicated software. I haven't been given permission to use this photograph, so I've blanked out the face enough so that the guy is not recognisable. But what I want to do is to take a look in and zoom in on some of the areas of this photograph. I mean, for instance, look at the beard, the texture of the beard. I mean, you cannot see any hairs there. In fact, the texture of the beard looks exactly like the texture of the headband around the top. Okay, yeah, it's a cartoon likeness, but it's not a photographic reproduction. Look, we can see all these funny shapes, these dots and blobs. So this is a 500 ppi image. There are very few single pixels on here. I mean, as I said, this is a very, very crude image, and this is what I'm really saying to you. There is no way that you could class this as photo engraving. I rest my case. Now, that doesn't mean to say this machine is no good. It's certainly not suitable for the purpose that I thought I was going to be able to use it for. I've got the two images here side by side. One is slightly different than the other at this point in time. They're both grayscale. This one's got oblong pixels in it. And what I should do to this one is just simply image, mode, bitmap, flatten the layers, yes, 254, which is the resolution I'm going to be using, because that's the size dot that I know I can produce on the machine. I might be able to go up to 300 or 350, depending on the line thickness at the speed I've got to use. But the line thickness or the dot size depends on the speed that I can run at. The faster I can run, the smaller or thinner the dots. So it's a bit of an experimental process. We've got to try and find out what size dots we can produce at the speed that we can produce a reasonable image. Now this is going to be done with a normal diffusion dither. So we'll now change this into a bitmap. So this time we'll change it to a halftone screen and 600 ppi. Okay. Now we use the numbers that we had before, 25 pixels, 25 lines per inch, 22.5, and the shape is round. And again, probably if I shrink that down, we shall find that there is a point where it looks quite reasonable, you see.
Well, here's my point about size mattering. Because I've made this a very big picture, it's only 254 ppi, and in fact it's not even 254 ppi, it's 254 lines per inch, but there's only 127 pixels per inch across, because if you remember, each pixel is double the width. So this is a very strange pattern, but because it's a large picture, it's pretty incredible, I have to say. I'm pretty pleased with this. Now, this is done using only 500 millimeters a second, which is the correct speed to get the pulsing right for the size of pixels and the frequency that we're using. Very strange combination, but if you get that combination right, look what you can produce. Now this is a 600 dpi image, done with the halftone screen method. I've got the lines per inch set quite coarse at 25 lines per inch. But hey, if I go much closer than that, this will become a real barbecue. Well, I don't think there's any doubt that my method on the left is somewhat better than the method on the right. If we zoom in and take a look at that one, you can see all the little pixel areas, all the little blobs that I showed you when we were looking at it on the screen. Look at the clarity of her iris there. And let me look at the same eye, which is the right eye, on the other picture. There's just no detail there at all. It's lost. Not only is it dark, the white is not white, because when I put my hand on here, everything feels sticky, and look, it just brushes off. I've seriously overburnt everything. There's no sticky feel to this one at all. For those people that are not familiar with my other series, what I'm using here to engrave on is something called beer mat card. Basically, it's pure wood pulp. It's as close as I can get to wood without a grain in it. Yeah, I know I can use MDF, but MDF is not wood. MDF is a composite material, and it's got some wood bonded into it with a plastic. I don't want to cut plastic. I want a stable, reliable material that I can use for comparison, and this is the material that I use. Now it's got very good burning qualities, and it acts just like wood. In other words, it will exude fumes and sticky resin, but there's no chance of the grain getting in the way of the image. We've just seen how the halftone screen method, if you get it wrong, it produces a barbecue. I mean, this is absolute rubbish, to be honest. Hey, and it also took 45 minutes to produce that rubbish, even though it was running at 1200 millimeters a second. My method didn't overburn. It ran at 500 millimeters a second, and it only took 12 minutes. What can I say? So that's what we're trying to emulate with the halftone screen. How close can we get to it? When we set the image up, I set it to 25 lines per inch, that grid pattern. Okay, we're now going to close the grid pattern up, which means the blobs are going to get smaller. We're going to change the grid pattern this time to 80 lines per inch. We're going to leave everything else the same. Not exactly the same, because I'm going to make one other change. We're going to leave the speed at 1200, but this time I'm going to halve the number of lines in the y-axis. Now I can't change things in the x-axis because that will be dependent upon the image, but what I can do is reduce the amount of overburning by, instead of scanning at 600 lines per inch, I can miss every other line out and do 300 lines per inch. Now technically I'm expecting that to make the image lighter, but at the same time, because I've increased the lines per inch of the grid, my blobs are going to be smaller. And if my blobs are smaller, it means the overrun on black at the end of each line, i.e. I get an extra pixel per line, or I lose some white in the image, if you like. Because the blobs of white and the blobs of black are much smaller, the effect of an extra pixel on a black blob is going to be greater. So on the one hand, I'm going to make it lighter because I'm going to use less lines per inch. On the other side of the coin, I'm going to be making it darker because I'm going to be changing the ratio of black to white significantly. It should only take maybe 20 minutes as opposed to 40 minutes. There's the original picture, just turned to grayscale. I'm going to carry out a couple of tricks that would normally be carried out by the big commercial bits of software. The first thing I'm going to do is to change the picture. So there we go. Now look, you can see how much I've lightened that picture. It's almost badly overexposed now as far as a photographer is concerned. Then we'll go in and we'll do another little bit of work on it. Filter, sharpen, unsharp mask. There we go. We'll exaggerate some of the features. Image, mode, bitmap, 600 pixels per inch, halftone screen. We've got the frequency set to 80 lines per inch now. We've still got 22.5. We've got round blobs. Now what I'm going to do this time, I'm going to change the from 0.20233, we're going to change that to 0.0466. We're going to leave the power at 60% because we want the colour in the burn. We're still running at 1200 millimeters a second. And we're still set on 25 kilohertz, I believe. Yeah, 25 kilohertz. I mean, to be honest, when you're drawing lines, it really doesn't matter about the frequency. It's better, but it's still no comparison with the one on the left. First of all, let's go back and take a look at how that was done. Bear in mind, those are double width pixels, and what I'm trying to do is to make sure that I keep the 1 pixel burn, which will finish up at 2 pixels, on the double pixel. Now, I'm going to leave that image as contrasty and dark as it is, because what I'm going to do now is try and lighten that image by changing the parameters. And let's show you what I mean. That were my original settings, 2500 frequency, 500 millimeters a second. We basically had a 0.2 pixel. And what we were doing, we were making sure that the pulse was only half the pixel, in other words 0.1. So by the time it got to the end of the pixel and turned off, it was into a gap. So if I change this to 1200 now, and I change this to, I think, I'm going to guess, I think it's probably going to be 6 kilohertz. Enter. I finish up with the same numbers, 50%. All right, so I can now run this. It's 2.5 times faster almost, so it should get lighter without me touching anything to do with the image itself. I still think it's obvious when you look at it from here which one is the halftone screen. It's the one in the middle. Now the one on the right is done at 2.5 times the speed of this one here. We didn't gain a lot because we took 12 minutes 30 for that one, 10 minutes 30 for that one. So even though we went 2.5 times the speed, we didn't gain a lot. But that's obviously because the overrun on that one at the end there was more. So there really wasn't much gain by going 2.5 times faster. To be honest, I think that's probably enough initial exploration into photo engraving. We've got many other things that we want to explore on this machine, but we've established a few very interesting principles associated with the machine through this photo engraving technique. I would urge you to go and look at some of the videos published by these, what I keep calling the big boys, and just see how they get on, what they do. It's actually, in some ways, I don't want to be rude to them, but it's very comical at times. They're not telling you what they're doing, they're not demonstrating how those parameters affect the picture. You know, you get all sorts of what I call techno babble. So I'm moderately pleased at the moment that I know how to get a half decent image off of this machine. So I think the next thing we'll do is to look at ordinary engraving, because ordinary engraving is, well, we've already begun to explore some of the problems with ordinary engraving here. The faster you run, the weaker the picture, as demonstrated by this one and that one. That's run at 2.5 times the speed, and look at it. We haven't got as much power into the material as we have on this one. So I think we can already begin to see the problem that we're going to have with this machine, and that is we're going to run out of power before we run out of speed. So thank you very much for your time and your patience, and I'll catch up with you in the next session.